Hello, this is Allison, and today we're looking at section 4.1 notes on polynomial functions and modeling. Our objectives for this section are to determine the behavior of a graph of a polynomial function using the leading term test. We also want to factor polynomial functions and use that factoring to find both their zeros and their multiplicities. And we'll use a graphing calculator to graph polynomial functions, find their real numbered zeros, the locations of their relative maximum minimum values, as well as their domain and range. And then finally, we're going to be looking at solving applied polynomial problems using a linear fit, a quadratic fit, a power function, cubic, or a quartic polynomial function to do some modeling of data. All right. Let's get started on those objectives. First, we've got ourselves a quick review about some operations here. If you had to add 2 grapes plus 3 grapes, hopefully you'll agree with me that you're going to end up with 5 grapes. And that leads us to the idea of the operation about adding like terms. Similarly, 2x plus 3x adds to 5x. And in the next one, 2x squared y plus 3x squared y is similarly going to add up to 5x squared y, since the variable portion is exactly the same for both x squared y's. So I'm going to end up with 5x squared y. In the bottom, if I'm attempting to add up 2 grapes plus 3 apples, there's no way to simplify that besides saying I need 2 grapes plus 3 apples. It's already simplified. Similarly, 2x plus 3y cannot be combined. It's going to stay as 2x plus 3y. And 2x plus 3x squared, these are also not like terms, so it's going to stay just as it is. So instead of being able to simplify, such as I was able to do on the top, the bottom ones are not like terms. Definitions. A key definition, I was talking about that word term a moment ago. So a term is a constant, a variable, or a product of a constant and a variable that might be raised to powers, such as the x squared part of that term there. In our terms, when we have like terms are either constant terms themselves or terms that contain the same variable raised to exactly the same respective powers. Unlike terms are going to be any terms that are not like terms. Okay. Continuing, a monomial is either a constant, a variable, or a product of a constant and one or more variables raised to counting number powers. So, for example, a monomial might be 3, that's a constant. Or a monomial might be x, that's a variable. Or a monomial might be 2xy to the third power. That's a product of a constant, in this case 2, and one or more variables with counting number powers. An example of something that is not a monomial might be 4x to the negative 2 power, because my exponent is not a counting number if it's a negative number. So I'm going to cross that one off with that negative exponent. Make sure we can see the negative that I crossed out there. That's just something that we would not consider a monomial. Right? Continuing down, we've got next polynomial. So a polynomial, or that's short for polynomial expression, it's either a monomial or a sum of monomials. We usually write polynomials so that the exponents of the terms decrease from left to right. That's what we call in descending order. So for example, a polynomial might look like 3x to the 5th plus 7x to the 4th minus 8x squared plus 1. I made that example up there. But I've got monomial terms. This one's just in a variable x. We typically are going to be working in single variable situations for most of this chapter. And it is in descending order because the exponents of the terms decrease from 5, 4, 2, and 0. It's okay if I skip some exponents, but they are decreasing in terms of the order of that term. Okay, the degree of the term is the exponent on the variable if I have a single variable. But if I do have more variables, then we're going to take the sum of the exponents on the variables. And the degree of the polynomial is the highest degree of any non-zero term in the polynomial. So for example, if I have a term such as 8x to the 5th, its degree is 5. That's the exponent. If I have a term like negative 4x to the 3rd, y to the 4th, its degree is going to be 7, because that is the sum of the degrees of the multiple variables in that singular term. As for another example, if I have the polynomial, which is going to be the top bullet for degree of the term, if I look at the degree of a polynomial and have, let's say, 2x to the 4th minus 8x to the 3rd plus 10, the degree of the entire polynomial is 4, because that is the highest degree of any of the non-zero terms. So the individual terms here have degree 4, 3, and 0, but the whole polynomial would have degree 4, the highest. All right, continuing on with our definitions. We'll talk last here about coefficients. So the coefficient of a term is the constant factor of that term, and the leading coefficient of the polynomial is the coefficient of the term with the largest degree. So for example, a coefficient, if I have about negative 8x squared, its, to abbreviate coefficient, is negative 8. Or if I have the polynomial negative x over 2, its coefficient is negative 1/2, imagining that there's a 1 with that x, so it's being 1 divided by 2. 1x over 2, negative, makes a negative 1/2 coefficient. If I have a couple of terms, so I've got a polynomial, not just a couple monomials. For example, 3x to the 3rd minus x to the 5th, the leading coefficient in this case would be the coefficient of the term with highest degree. And so in this case, it's that negative 1 on the x to the 5th term. It's not in descending order, so I could rewrite this as negative x to the 5th plus 3x to the 3rd, and the leading coefficient is still that negative 1. All right. A couple of examples to familiarize ourselves with the terms for polynomial functions and modeling. Let's take a look at the next page. Topic 1 is on here. We go, polynomial functions. So in general, we talk about polynomial functions in one variable in the following manner. So a polynomial and function in expanded form is given by p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on down to a sub 0. In this polynomial, the coefficients are represented by a sub n minus 1, and so on. And those coefficients are real numbers, and then each of the exponents, n minus 1, and so on, are whole numbers. This notation with the n, and then n minus 1, and then n minus 2, and so on, this would be x to the 1, finally, and then x to the 0 is our constant term right here. This notation is used just to show that this polynomial is in descending order. N is the highest because n plus 1 must be lower than it. N minus 1 must be lower than n. So it's in descending order to start with degree n. So this is the definition of a polynomial whose degree is n. I'm going to make a note of that. The degree is n for a polynomial in this form. Okay, so we're already familiar with several families of polynomials by degree. So we've got our constant function, f of x equals 2. We make a sketch of this graph. It's a constant function that's going to have y coordinate 2, so 1, 2. And the degree of this is 0. The leading term itself is 2, since there's only one term. And the leading coefficient is 2, because that is the numeric portion of that term. Degree of 0 because x is raised to the 0 power. There are no x in that term. Okay. On to the next one. We've got ourselves a linear function. In this linear function, it's kind of hard to read. I'm going to assume that this is a 3x plus 2 here. And I want to make a sketch of this graph. So that's where 2 would be. I'm just going to give it a slope of up 3 over 1. So a quick little sketch right here of what that function might look like. The degree is going to be 1, since I have x to the first power. The leading term is the full 3x. And the leading coefficient is the multiplier 3. Okay, so we've got constant, linear, quadratic. Quadratic, we've got ourselves the x squared minus 1 function. We know this is a parabolic shape, and it's going to be pulled down, a transformation of down 1. So the shape of this graph is going to look like this. Its degree is going to be 2. That's the exponent that is highest. On a leading term, that is x squared, and the coefficient of that term is 1, a multiplier of 1 times x squared. For this next one, this cubic, I can't see what was supposed to be in this box, unfortunately. I'm just going to pretend it was a plus 1 here. This is right in a 1. And let's make ourselves a quick sketch of this graph. If I'm saying it's plus 1, then I know I'm going to have a vertical shift of up 1. And a cubic function usually starts low, switches up in this direction, but I have that negative reflection to reflect across the x-axis. So we know we're going to switch down. So that's our cubic. The degree of this cubic is 3. The leading term is negative x to the third power, and the leading coefficient is that negative 1 multiplier. Last, we've got ourselves a quartic. Now, this function, again, was trimmed off on accident. So I'm going to rewrite the function below. I'm going to assume this was supposed to have an x to the 4th at the end of it, because if it's just x squared to begin with, it's not quartic, it's quadratic, so we're missing that term. So we're going to assume that this function, q of x, was meant to be x squared plus 3/4 x to the 4th power. We'll make ourselves a graphical sketch. It's not in descending order if this is the way the function's written, because the first term is not the term that has the highest power, but it is a 4th degree function. So it has a positive coefficient, so it's going to be facing upward. It is a little less than 1, which is a slight widening indication. And then it's got another term so that may reposition its vertex. In this case, without having an up or down shift, it is going to have 0, 0 as one of its coordinates. So we're going to draw it that way. So let's draw this one as a wide. It's mostly a parabolic type shape. I'm not 100% sure because quartics could look like wide parabolas. They also could have a dip to them and look like W's. So I'm not 100% sure which of these two this graph is going to look like with this extra term. In order to narrow that possibility down and see which of them it is for sure, I'm going to need to graph it with a graphing calculator. So I'm going to look at just these right now, and we'll talk further about how to distinguish between those characteristics and then using technology to assist. But right now, one of those two shapes is my guess for this quartic. The ends do have to go in the same direction because the degree is even. That degree is 4. The leading term, it's not written first, but it is the 3/4 x to the 4th, and that coefficient is the 3/4. Okay. Note, there are many functions that we will see that are not polynomials, but these are some that are polynomials. Some examples of things that are not polynomials are things that have negative exponents, as we saw an example of earlier. Also things that are exponential or logarithmic, or those upcoming sections that we'll get to in chapters 5, 6, and 7. To talk about polynomials, polynomials are especially handy for modeling real-world situations for two main reasons. The first reason is about their graphs. The graphs of any of these polynomial functions are connected or continuous. When you draw a polynomial, there's no numbers that are not part of the domain of that function, which we'll write down here as well. So the graphs are connected or continuous, and their domains are all real numbers. Or negative infinity to infinity. That's going to be true of any of our polynomial functions. That's one of the reasons that they're handy for modeling, is I have no problem areas in the domain or on the graph of the function. Topic 2 is the leading term test. The leading term test is useful for describing how the function behaves in the long run, aka the ends of the function. So the leading term test says that if a sub n times x to the n is the leading term of a polynomial function, then the behavior of the graph as x approaches infinity, so for very large inputs, or as x approaches negative infinity, very large negative inputs, can be described by one of the 4 following ways. This is often known as the polynomial end behavior. First, if n is an even number and a sub n is greater than 0, I'm going to have the case here where n is even. We're going to have the typical parabolic shape, or maybe a W shape. Could have more bumps than one W if it has a higher enough degree. But those are the general types of shapes we're thinking right here for an even degree with a positive leading coefficient. Main point here is that both ends are going to go up. Okay, so both ends go up. And the more formal way to say that is as x approaches infinity, the function f of x approaches infinity. That would be talking about the right-hand side for thinking about for very large x values. Very large x values increase to the right. And on the right side of this graph, the graph is going to go infinitely large. So that's the first point. The second is as x approaches negative infinity, so that's our left side. We'll see that on the left side, the graph also goes up. So on the left side, f of x also approaches positive infinity. It's going to approach positive infinity on both sides because the ends go in the same direction. Continuing, if n is even, but the leading coefficient is less than 0, negative, we can picture this as an upside down parabola or upside down W type shape. In this case, it's even, both ends go in the same direction. So both ends are going to go down. Oops, both ends go down. So more formally, we would say that as x approaches infinity, f of x approaches negative infinity. So that's talking about the right-hand side behavior of this graph. And similarly, as x approaches negative infinity, f of x also approaches negative infinity. So again, as x approaches negative infinity, that says left side. Left side, we're going down just like we were for right side. Now let's look at the odds. In the odd function, when n is odd, we're going to look at, again, both positive leading coefficient and negative leading coefficient. If my leading coefficient is positive, we're going to have either a shape like x cubed, or we could have a shape that bumps up and down like x to the fifth, or an x cubed graph that's got a few more wiggles in it. The ends go in the opposite direction, but we need to specify how. So first, as x goes to positive infinity, that's right side, that's our right side, our end on the right is going up, so our output goes to positive infinity. But on the left, as x approaches negative infinity, that's the left. On the left side, as x gets large negative, our ends go down. So f of x goes to negative infinity. If you've got a negative leading coefficient, that's going to reflect. So your graph's going to look something like one of these. It's been reflected. Again, the ends go in opposite directions. And as x approaches positive infinity, that's the right side, positive infinity, the ends are going down. So f of x is approaching negative infinity. And as x approaches negative infinity, that's the left side. This time on the left side, we're going up. So as x approaches negative infinity, f of x is going to approach positive infinity. So each one of these is different, and it's a way of describing the shape and what is happening at the ends based on whether or not your degree is even or odd and your leading coefficient is positive or negative. So if I look at an equation like these in example 1, I can use the leading term test to predict the end behavior of these functions. In the first one here, the leading term seems to be the term that is first. Just be careful, it might not always be the term that is first. It seems to be this term right here. That is a term that is got an even degree and a positive coefficient. So we have n is even and a sub n is greater than 0 and 3 is positive. So that means as x approaches positive infinity, an even degree, positive coefficient, my right end is going to go up. And as x approaches negative infinity, the left end is going to go up as well. So usually are in this kind of shape or W shape, one of these two shapes. The shape itself doesn't matter in terms of how many bumps it has because we're talking about end behavior, and the wiggle is in the middle. We really just want to know what the ends do. And on both sides, they go up. In the next one, part B, if you look closely, the leading term is over here in the middle because that has highest degree. So in this case, the degree n is 3, so it's odd. And a sub n, the coefficient, that's negative 6, so it's less than 0. So we're in this case right here. So we know that as x approaches positive infinity, f of x is going to approach negative infinity. So on the right side, we're going to go down. And also, as x approaches negative infinity, f of x is going to approach positive infinity. On the left side, our graph is going to go up. So we're looking at this type shape. I can tell that just from looking at the leading term from each of these, the leading term test. Type 3 is about finding zeros of factored polynomial functions. If we recall, we know that for any two quantities A and B, if A times B is equal to 0, then A equals 0 or B equals 0. So if we've got a polynomial we want to find the zeros, we're solving for when f of x equals 0. And that's going to happen if, in this equation, 5 times x minus 2 times x minus 1 times x plus 1 equals 0. And that'll be equal to 0 if any of the multipliers, a and b, or in this case 5, x minus 2, x minus 1, and x plus 1 are equal to 0. 5 does not have a variable, so 5 can't be 0. So we'll start with the first one that has a variable. That's the x minus 2 factor. So x minus 2 can equal 0, x minus 1 can equal 0, and x plus 1 can equal 0. From those, we'll get the three solutions. Add the 2 over, x equals 2. Add 1, x equals 1. Subtract 1, x equals negative 1. So there are 3 zeros. X equals 2, 1, and negative 1. And the order on these does not matter. You could have written them as negative 1, 2, 1. I just wrote them in the order I found them. Part A was already factored, so when it's factored, it's really convenient and easy to find the zeros. Just pull each of the factors apart and solve. Part G is not factored, so I could factor it myself if I wanted to solve g of t equals 0. So we're looking at solving t squared plus 4t plus 4 equals 0. That's going to factor as, see, I need to multiply to 4, so 2 and 2, add to 4, which is perfect. It's going to factor as t plus 2 times t plus 2. 2 times 2 is 4, 2 plus 2 is 4. And so if I solve each of these, t plus 2 equals 0 is my first factor, and t plus 2 equals 0 for my second factor. I'm going to have t equals negative 2 if I subtract the 2 over, and again t equals negative 2 if I subtract the 2 over. When I get two answers that are the same, I don't need to list them both. I can just say t is equal to negative 2, but I can say that has a multiplicity of 2. Multiplicity 2 means I got the same solution twice. You can have multiplicity of 2, 3, 4, 5, and so on. If you get the solution just one time, they do have multiplicity 1, but it's not necessary to say the multiplicity unless it is a number that is not 1. As I was saying, in that example, we got a 0 of multiplicity 2. And that does mean that we would have been able to rewrite the function in factored form as, so we had g of t equals t plus 2 times t plus 2 from the previous page. I'd have been able to rewrite that as t plus 2 quantity squared, since I have the same factor twice. And that multiplicity 2 corresponds with the exponent on the factor as well. Okay. More about multiplicity, even and odd multiplicity. If a polynomial has a factor of the form x minus c to the kth power, where k is bigger than 1, and k plus 1 is not a factor, meaning it goes in k times at most, we can determine that if k is odd, the graph is going to cross the x-axis at the 0 formed by the number c, and if k is even, the graph is tangent to the x-axis at the point where you have c as the value. What we're thinking about there by tangent means that the graph is going to touch and then turn around at that c value. This would be an example of a point that is tangent to the x-axis. It touches it just in that one place and only that one place, as opposed to a graph that went through in some fashion at that c value and crossed. So odd, we are going to be crossing the x-axis at that value versus tangent, turning around instead. We know that the locations where the graph touches or crosses the x-axis are the x-intercepts. And these are also the zeros, like just the real ones, of the function, along with the ideas of multiplicity and complex numbers. An important realization emerges about polynomials and their factors. If a polynomial function has degree n, which is larger than 1, then it has exactly n zeros, as long as we're counting with multiplicity. These zeros are all complex numbers, although some may be only real, and we see the real zeros as the x-intercepts on a graph. A variation of that statement is referred to as the fundamental theorem of algebra, and that theorem says that every polynomial function with real coefficients can be uniquely factored into a product of linear and irreducible or non-factorable quadratic factors. Okay. In topic 4, we're going to find some real zeros with a calculator. Some polynomial functions, most actually, can be complicated and might not factor nicely. And in these cases, we can rely on a calculator to find the real zeros. First question is, how many zeros does this function have? Well, I can see that its degree is 3. And so it has got to have exactly 3 zeros, that is the degree, counting multiplicity. So it is going to have 3 zeros because it has degree 3. Use our calculator to locate the real zeros and explain any discrepancy. Okay. One second, my calculator come off over here. All right, so on my calculator, we're going to graph this function. F of x equals 0.1 x to the third plus 0.3 x squared plus 0.1 x minus 0.3. Okay. Now, when I first looked at it, it looked like it might have a 0 right here, but if I zoom in a little bit, I'm going to see that was a maximum point, not a 0. So the 0 seems to be here. And I don't have any others because 0 needs to be an x-intercept. I've got a y-intercept. I've got other points along this graph, but I only have one place where it crosses the x-axis. So I have a 0 at, there seems to be one real 0 at x equals 0.769, and that is the only 0 that I can see. Because I can see it, I know that it's real, but there certainly are 3 zeros, so it means that the other 2 that I can't see, I'm pretty sure they're not just somewhere else. This function doesn't turn around later out of the window that I was originally looking at. So the other 2 that I'm not able to see must be imaginary. All right, so I don't know them. I would need to use a different method in order to attempt to find them. There's only one though that is real I'm able to find using the calculator. Okay. Topic 5. We're looking next at fitting polynomial models to data. And in this example, we're going to let P be the percentage of professional baseball players who report having used smokeless tobacco at T years since 1990. Fill in the missing table in the column, label the scatter plot, and then sketch the line that best models the data. All right. I need to work in T years since 1990. So 1997 is going to be 7 years after 1990, so it would have a t-value of 7. 98, we have a t-value of 8. 9. 2000 is 10 years after 1990, so 10, 11, and 12. For labels, on our independent or dependent axis here, the y-coordinate, those are going to be in percent. And this is going to be in years since 1990. More full label right here might say percent of professional baseball players who reported using smokeless tobacco. So I'm going to highlight that since I'm not able to squeeze it in that space. Percentage of professional baseball players who reported using smokeless tobacco. That is the full dependent variable that we're talking about in this situation. All right, so we've done part A. Part B asks us to sketch a line that best models the data, i.e. comes close to the point. All right. Now, it looks like there's a little bit of bump in these points. It's not going to be perfectly straight, so we get a ruler. Even though it's not perfectly straight, it is close to a line. So with a ruler, I might be able to get an approximation, trying to find a line that fits the visual center of this data. The points on the left seem to be pretty close. A little more variation on the right, so I'm trying to be pretty close to the ones on the left and kind of split the middle on the right. Let me draw this line and see how we did. Okay, it'll be something like this, where we're pretty close to the data, but it's kind of hard to, by hand, visually draw ourselves the perfect graph. Our calculators, on the other hand, are really good at this. So we're going to do the best fit, aka regression model, for several types of polynomials, and we're going to use those to make predictions. The quality of the regression can also be measured by the R-squared value, which is called the coefficient of determination or coefficient of correlation, depending on what language you're using there. In order to use this value, you want it to be close to 1. You're thinking about your R value as a percentage, so close to 1 would be close to 100%. So if R squared equals 1, your model is 100% accurate. Okay. So let's take a look. We've got some directions below, but we're going to do the regression model for this data. Okay, so clear this, making a table. And I need to enter my values here, 7, 8, 9, 10, 11, and 12. And then 9.7, 8.8, 8.5, 7.5, 8.0, and 6.5. I zoom over on that data. This is what it looks like in the window. That is my zoom fit window. I can zoom it out on this a little bit to adjust the window if I want to. And if I wanted it to look just like the one on the paper, I could manually rescale. So I could see on the y-axis from 0 to 12. And then it looks like the x-axis on this one went from 6 to 13. And with that window, we're able to see that the data looks quite a bit like the data presented on this graph. Okay. Helps us verify that we typed our values in right. All right, there are a couple of ways to do the regression. One of the ways is to enter the regression statement. Y1 is approximately mx1 plus b. That just comes from the fact that a linear model is y equals mx plus b, that's slope-intercept form. So we change the y value to y1 if your table has a y1 in it, you're using table 1. If your table has a y2 in it, then you would use a y2 here, of course. We're going to change the equals to an approximately symbol so that we can approximate a model since we know it's not going to be perfect. We use m to calculate the slope. We use x1 to correspond with the x1 values in the table right here. So m, x1, and then plus b stays the same. So those couple of little changes right here from the basic form of the equation will help us remember the way to write the regression model. Okay, so this is my equation. It seems to fit similarly to the line I was able to rough out and draw by hand. It's pretty close to all the points at the top. We notice there's just some more variation here, and it fits the middle, which is what it's supposed to do. Okay. The other indication of goodness or quality of the regression model is based on the R squared value, which is 0.8795. The closer that is to 1, the better. So that's at like an 87% accuracy if you can consider it as a percentage. It's pretty close to 1. 87 is pretty close to 100%. So our model fits good. It's okay. It's not perfect. It's not great. We're not in the 0.9s, but we're in the 0.87s. So it's pretty good. Okay. Okay, so I'm going to write my model down here, and then I'll talk about this line right here. So my model, it says P. I'm going to call it P instead of Y. I'm going to use P of T equals. And I found the slope value. Let me make this bigger. The slope value, the number for m, given to me as negative 0.554 times my independent variable, which is t, plus the b value, which is 13, 0.432. So this is our model. And we know that this model has an R squared value of 0.8795, which is pretty close to 1. If I needed to, I would use this model right here to be the equation for this line that is the line that best fits this data. All right. Now, I want to go back and read this sentence here. There are two main types of predictions. There's extrapolation and there is interpolation. Can we talk about those? Extrapolation is when you make a prediction that is outside the edges of your data. Extrapolation means that your prediction is outside the data. Anytime you make a prediction beyond the data, either before the data started or after the data ended, that kind of prediction is less reliable. And the reliability is going to fade the further away you are. So your reliability might be sort of strong in the middle, but it's going to fade the further away you get from the data. Less reliable the further away. All right. As opposed to interpolation. Interpolation is for predictions that are made within the boundaries of the data, and that does mean between the first data point and the last data point. First being 7 for this particular data set, last being 12. Any prediction made in between those years is an interpolation prediction. And these are predictions inside the data. And they're generally more reliable. As long as you've got a good R squared. They're just as reliable as your R squared. Bad R squared value means they're still not reliable. A bad R squared would be something that was below a 0.7 or 0.6, not as close to 1. Certainly anything below 0.5 is further from 1 than it is close to 1, so you would not have reliable predictions with a low R squared. All right. Our last page here, we've got another set of data. This one is on fuel economy for a Camry. And we're going to plot this data and figure out what kind of model to use. Clear this graph. Make a table. Okay, so let's enter, got the X values, get the Y values here. And zoom. So this data does not appear linear like the last data set where a straight line seems to be the best fit. This has at least one turnaround point, so I'm thinking quadratic is probably going to fit it. I really only do see one turnaround point. I don't see evidence for 2 or 3 turnaround points, so we'll stick with one turnaround point. And we're going to make a note of this right here. What kind of polynomial model appears to be best? Quadratic appears to be best because the data seems to have one turnaround point. one turning point. So we're thinking that something of this shape should fit that data pretty well. Right. It's also important to note that it's always good to use the simplest model possible. I'm going to use a quadratic because it has one turning point. If I used a cubic, it might fit the data better, and it will certainly have a higher r-squared value, because as the degree increases, the r-squared value does automatically as well. But that doesn't mean it's better. We want to use the simplest possible model for each of these. In this case, with one turning point, that simplest possible is going to be a quadratic. I know that a quadratic equation looks like y equals ax squared plus bx plus c. So a quadratic regression is going to look like y1 approximately a times x1 squared, changing x to x1, plus b x1 plus c. So y1 approximately ax1 squared plus b x1 plus c. Okay, this model, the variables here were m for output and v for input. So m of v equals, the a value is negative 0.170. I missed a 0. Sorry about that. Let me squeeze that in there. As you can see, it was supposed to be negative 0.017 times b squared plus 1.905 b minus 24.864. Move my calculator out of the way. I'm going to rewrite that so you can read it down here. It was supposed to be down here. So negative 0.017b squared plus 1.905b minus the 24.864. A few questions about this model. A friend of yours drives a 2012 Camry and wants to know how fast to drive on the highway to get the best gas mileage. So to get the best gas mileage, the question asks what our model suggests. And remember, the model is the equation. What we found up here was the best fit model. The model is the equation. So I'm going to turn off the data for a second and look at the model's prediction. The model predicts that I get the best fuel economy at its vertex point, and that's going to be the point 55.976, comma 28.443. In other words, that means that at a speed of, the speed is the velocity, the input, so at a speed of 55.96, or approximately 56 miles per hour, the friend gets best fuel economy of about 28.4 miles per gallon. In contrast, notice that in the table, we do get to 30, it looks like, as the highest value at 55. And we're saying that we're only going to get to 28. this is what our model predicts. So the model has a bit of error, as it always will, compared to the data, and that's okay. Did the model get close? Yeah, it was pretty close to 55. It said 56, so we were close. Did it get us pretty close to 30? 20.4 is closest. So again, the model was doing a fairly accurate prediction. There's going to be some error, and if we take a look at our R-squared value, it's 0.93. So it's not 100% accurate, but it's going to get us close, and it will help us make good predictions for other values. They won't be perfect, but they will have some sense of reliability as far as closeness. All right. Use your model to make a few predictions, and then what kind of prediction is each? Okay. I'm going to enter this model here so that I can use function notation. So M of V is equal to negative 0.017 V squared plus 1.905 V minus 24.864. I just typed in the model so that I'd be able to use function notation, and this way I can evaluate M of 2, M of 43, and M of 75. Okay. So when I plug 2 in for the input into the function, I would get an output of negative 21.12. When I plug in 43, I get an input of 25.62. And when I plug in 75, I get an output of 22.39. Okay. What kind of prediction is each? All right. The data set here had input values that went from 30 to 70. So 2 is beyond the edge of this. So this one is definitely going to be extrapolation. "43" is in between data values, so that's interpolation. And 75 is past the end, so that's another extrapolation. If we think now about what each of these is telling us, at 2 miles per hour, the fuel economy is negative 21 miles per gallon. We know that doesn't make sense. But at 43 miles per hour, the fuel economy is 25.6 miles per gallon. That's within reason as far as that comparative values from near data points. So that's within reason. So that would make sense in context. 75, if it was 25 miles per gallon at 70, it's within reason to predict that it might be 22 at 75, 22 miles per gallon at 75. That's still extrapolation, but that extrapolation is near because 75 is relatively close to 70 within the span of this data, but 2 is quite far away from the 30 previously, right? That's quite far away. And you can see that the further away we get in extrapolation, the less reliable the prediction is until that prediction just doesn't make any sense. Okay? So that's going to be an invalid prediction or model breakdown. But hopefully you agree with me that the interpolation and the near extrapolation predictions both make sense in this context. Try using a higher degree polynomial to model these data. What happens to the r-squared value as well as the predictions from part D? All right, so I did use the quadratic here. We copy that and paste it. I might change this now to a cubic. So a x1 to the third, b x1 squared plus c x1 plus d. Let me turn the data back on. All right. So the cubic model looks roughly quadratic within the realm of the data. Its other turning point is out here at 11 miles per gallon, which we don't have any data about. So if I'm looking just at r squared, the r squared for the quadratic was 0.93, but for the cubic it's 0.95. So it does look like, hey, maybe cubic is better. It's got a higher r squared value. Problem is that's going to happen absolutely every single time that you increase the degree. That does not mean that this model is better. It means it has a higher degree. That's all it means. Because the second turning point is outside the edge of the data, this model has increased complexity that the data just doesn't need. So cubic isn't better than quadratic because it has the same shape within the data. I could do the same argument for a fourth degree. Let's copy this one again. Change it to a fourth degree. Oops, that one give me a third degree term. This one's going to be a second degree term. And it's 1. And capitalized, of course. It's not Euler's number. Once again, higher r squared, and once again, within the data, between the first data point and the last, the model is quadratic looking. The two additional turning points are outside the edges of the data, so it doesn't add any aids in terms of the data. So it's unnecessary to increase the degree. So quick notes on paper here. So r squared gets higher as the degree gets higher. But that does not mean that the higher polynomial fits better. We need to look at turning points. This does not mean that the higher degree fits better. Okay, so we need to look at turning points and end behavior.